right, so we're going to work out the matrix elements for this bilinear coupling, alpha 1, 2, Q1, Q2. And what we mean by the matrix element, of course, is NM, the operator, the product of these two things, and then N prime to M prime we will have on the other side, right? And we're going to have the factor out, the multiplicative factor, alpha 1, 2, divided by 2. The factor of half comes from the square root of 1 over square root of 2 in each of these Q1 and Q2. All right, so then we get A1, A2 plus A1, A2 dagger plus A1 dagger, A2 plus A1 dagger, A2 dagger, N primed, M primed. Right? That's the matrix element. And we're going to work that out. It's going to be delta functions, and we're going to have some constants, and then we're going to identify where the elements are in the matrix, and then we're going to add the elements for the diagonal part that comes from the individual uncoupled harmonic oscillators. Okay, so this is equal to all the constant stuff again. And what we're going to do is we're going to write down the terms. We're going to go from right to left, right? So we're going to have A2. Remember, A2 dagger makes M primed go up. A1 dagger makes N primed go up. All right, so for the first term here on the right, we're going to have, I think I'll do it down here, okay? We're going to have N primed plus 1, M primed plus 1. That's what this does to this. Then we get a multiplicative factor, the square root terms, right, which is going to be the square root of N prime plus 1 times the square root of M prime plus 1, and we'll put it both inside the square root. All right, so that's the first term. The next one over, we'll have over here, all right? And that's going to be A2 makes M primed go down, and A1 dagger makes N primed go up. All right, so we're going to have N primed plus 1, M primed minus 1. That's the new vector, and then the square roots that we get are going to be, for the A dagger, it's the one we're going to, so N primed plus 1, and for the M primed, it's the one we started from. Remember, it's always the bigger of the two. All right, that's our multiplicative term for that one. All right. Then we have this one, which I'll just do the one on the left here. So it's going to be both going down 1, and then both getting the square root of the higher state. So that's N squared M primed, square root of that. And then the vector part is N primed minus 1, M primed minus 1. All right, so that's the first one. And then the second term is the A2 makes M prime go up. Right, so N primed goes down. So N primed minus 1, oops, and then M primed plus 1. Then the square root part is going to be on the N primed because it went down, and then times M primed plus 1. All right, so that is working out what the operators do. Now we just have numbers and we have these vectors. We know that these are the NM are going to come across and give us delta functions. So we have alpha 1, 2 divided by 2. For the first term, N primed, M primed, we have delta N, and then N primed minus 1 for the first delta function. The second delta function is M primed minus 1. All right, for the second term, we have N primed times M primed plus 1, delta N primed minus 1, delta M primed plus 1. This is very tedious, and it's really hard to do it without screwing up. All right, the next one is M primed, N primed plus 1, delta N n primed plus 1, this, and delta m, m primed minus 1. Then we have the last term, n prime plus 1, m prime plus 1, delta n prime plus 1, delta m prime plus 1. Okay, so that is the full matrix element for the bilinear coupling. The whole Hamiltonian, of course, is going to be the sum of these. This sum of the matrix for the potential plus the matrix for the uncoupled individual harmonic oscillators, which will be diagonal. Okay, so let's work out what the terms are in the off-diagonal for the matrix. And what you're going to see is a kind of a remarkable pattern. All right, so the V matrix. Now, in principle, there's an infinite number of harmonic oscillator states that we need to consider. In practice, of course, you pick it to be finite. So what I'm going to show you is the first 4 by 4, and then we're going to see that it keeps going, of course. And the reason why I'm picking the first 4 by 4 is because that's where you're going to that's where we're going to see the box pattern that we're looking for. Remember how we're listing the states 0, 0, 0, 1, 1, 0, 1, 1, and then dot, 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 because there's no end to this. 0, 0, 0, 1, 1, 0, 1, 1, and then dot, dot, dot. So we're going to do the same thing. We're going to make a little grid. Now, fortunately, most of the matrix elements are 0. We'll take advantage of that, of course. You don't see any deltas in here where the two indices are the same. So all the diagonal elements are 0. All right, that's good. And then dot, 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 zeros. And then what else do you notice in the pattern here? We have cases, for example, here, where n prime, the one on the right, so if we do left, right, then the one on the right is going down. All right, so m primed, which is on the right side, which would be this one here. It doesn't really matter which way. The symmetric is going to be completely symmetric regardless. All right, this is where they both go down. All right, so the second side. So if we imagine a matrix element, this matrix element here, let's make it more explicit what we're saying. If the matrix element in the box, it would be equal to, so the first one will be, so 0, 1, H, or V, whatever, and then this is 1, 0. So we have the ket side and the bra side over there. Right? So make sure that that's clear what I'm talking about. All right, so m primed, mind you, is this. This is m primed, and this is n primed. All right, so what this is saying is, do we have an element, do we have a matrix element where n goes from 0 to 1, so that n primed minus 1 is equal to n primed minus 1 is equal to n. Okay, so that's this delta function satisfied. Here we have m primed minus 1 goes to m, right? So this term does not contribute because this is the same as this one, would be the same as that one, right? So that's not this term, but there is another one which has this pattern, okay? So here we have n prime minus 1, so that satisfies this 0, 1 for the n's. And here is m prime plus 1, so m goes up, right? So that's going to give us this term here. So what I'm going to do is I'm going to call this term, I'm going to give it like a shape. I'm going to call it diamond. All right, so blue is actually going to be diamond. All right, well, maybe we'll make it square then. I didn't think about doing it this way when I was writing my initial notes. So this is the square term. All right, then there's going to be another term, right, which we could probably call the diamond. All right, here what do we have? we have exactly the backwards one. And where's the backwards one for this? Well, it's right here. N primed is greater than N. No, N primed is lower than N, and we have to add 1 to get to be whatever N is. Here it's the other way around. All right, so the diamond pattern, the diamond entry is going to be 1, 0, V, 0, 1. All right, so that's what's going to go in that element, a term like this. Now, what else do we have? Well, we also have terms where they both change by 1 in the same direction, right? So here, M primed is going down, N primed is going down. So that for up to the 1, 1 case, that means that M primed and N primed have to be bigger, so they have to be 1. Right? And they go down, so that would be over here. We can call that orange something or other, orange triangle. Okay, and then the other one, of course, is the one up here, which will be related to that, so we could call that upside down triangle. Okay, so those are the non-zero elements up to this, and of course it continues, and there's going to be other non-zero elements as long as they have this pattern that they differ by 1. Either one goes up, either one goes down, flip-flop, or they both go up and both go down by 1, and that's going to repeat over and over again. But that's going to have the main impact on higher lying energy states that we probably do not study with normal linear spectroscopy. Okay, so what numbers do we put in there? Well, actually, it's funny because these all look very complicated, but if you work them out, you'll see that they all end up being a 1. Right? Every single one of them. So if I take the triangle one here, right? So N primed and M primed are both 1. That's this size is the prime side. So we get a square root of 1 times 1. That's 1. Here it's going to be 1 times 0 plus 1. So that's going to be 1. Here it's going to be 1 times 0 plus 1. That's 1. And it's going to be 0 plus 1 times 0 plus 1, also 1. So all the numbers that actually go in there are the number 1. Of course, out front, we have the alpha 1, 2 divided by 2. And the rest of these elements that we see in this particular window of elements are all zeros. But they're not zeros forever. They're just zeros in this sub. And if we go on to the next sort of chunk of them, we'll start to see another anti-diagonal, and there'll be this pattern of anti-diagonals increasing as we go. All right? Very good. Now what we're going to do is add to this the harmonic part. Right? So let's add the harmonic part. The harmonic part's, of course, pretty easy because we know that the harmonic part is going to be diagonal. So that means this element, for example, will be the 0, 0, H naught, like H1 plus H2, 0, 0 element, right? Which is just equal to the energy of the ground state of one oscillator plus the energy of the ground state of the other oscillator, right? Then we have here 0, 1, 0, 1. Right? And we know what that is. That's the energy of one excitation. This is the energy of another excitation, the same number. All right, so what we're going to do is we're going to just we're going to list our numbers, our energies for the uncoupled oscillator. We'll call this epsilon 0. We'll call this epsilon 1, epsilon 2, and so on. All right, so when we do that, for the full Hamiltonian, all right, I'm just going to, I need some place to erase. All right, so for the full Hamiltonian, we're going to have H1 plus H2 plus V, but I'm only going to do the first, these elements here. So we're going to have epsilon 0, but there's 2 of them, right? So that's going to be 2 of those. Then we're going to have here epsilon 0 plus epsilon 1. Which is the energy of the first state. This is the same thing, epsilon 0 plus epsilon 1. And here 1, 1 is just 2 times the epsilon times the energy of the one state. Now it does keep going on. We know that. Then we add in our off diagonals, and we see we have alpha 1, 2 divided by 2, and alpha 1, 2 divided by 2. We also have, on this one here, alpha 1, 2 divided by 2, and up here, alpha 1, 2 divided by 2, and we have 0 everywhere else. All right, but if we remember, what this looks like is exactly the same as or very close to exactly the same as what we had for the case of where we had two-level systems that were coupled together. Okay, and so what we can do is make our box here. And what we see is a pattern that's exactly the same as when we had two coupled two-level systems. Amazing, huh? So if we set the minimum of energy to be, if we set epsilon 0 equal to 0, and we only consider the excitations from there, then our Hamiltonian would reduce for the 2 by 2 subset, the blue part of the Hamiltonian would be epsilon 1, or just plain old epsilon if we want to be the one excitation of the oscillator. And then we have the coupling term, which will, in this particular case, is alpha 1, 2 over 2, alpha 1, 2 over 2. All right, and so then what we know happens is we calculate the eigenvalues and the eigenvectors of this, and we know exactly how that's going to work out because we've already done it. We have the initial energies. Wow, that's not flat. The initial energies that corresponds to epsilon 1 above the ground state. The coupling, they're going to split. One goes down by alpha 1, 2 divided by 2, and one goes up by alpha 1, 2 divided by 2. So that the energy gap between the two is literally alpha 1, 2, the coupling parameter. All right, now, what about the eigenvectors? You can relatively straightforwardly find when the two energies are the same, we get perfect mixing between the two of them. All right, and so one of the energy levels, I think it'll depend on the signs of these alphas. One of them will be, okay, so if alpha 1, 2 is positive, then the subtracted eigenvalue will be the lower energy one. And so we can call that the minus state, and that will be minus 1, 1, normalized, of course, the so-called antisymmetric stretch. The higher one will be 1 over the square root of 2, 1, 1. That'll be the symmetric stretch. Okay, and what's interesting about that is, of course, there's a sign of alpha, right, that we don't necessarily know. It could be positive, it could be negative, depending on what the physical actual system is. And so what we can do now is we can ask ourselves which of the stretches is actually lower in energy. So for CO2, for actual carbon dioxide, the stretch that we can see in IR spectroscopy, there's two: the bending vibration around 667, and the stretching, which is around 2300. The antisymmetric stretch is around 2300 wave numbers. And that's the antisymmetric. And the symmetric stretch is around 1300 wave numbers. That we don't see in IR spectroscopy because there's no change in dipole moment from this. But you can determine it from Raman spectroscopy, which doesn't have the same selection rule for dipole moment, right? And so then this tells us that the symmetric stretch is lower in energy, all right? And in fact, that tells us then that alpha 1, 2 is negative, if this is the way that we want to think about these two molecules. So it will be the bilinear coupling term is negative. Now, it turns out, of course, that CO2 is not just bilinearly coupled. There's going to be an enharmonicity to it. But you can't tell that if all you do is go and measure the two frequencies that you get from IR spectroscopy or Raman spectroscopy. When you do CO2, you can't tell what the other higher lying excited states are. If you knew what the higher lying excited states were, then that would let you figure out the rest of the parameters. For example, the diagonal and off-diagonal and harmonicities. So if you want to have more information about the potential energy surface, in this case, we have the simplest possible case that will cause the splitting. You need additional information than just the frequencies of these two transitions here. All right, and so that's where nonlinear or higher order spectroscopy is handy. Now you could say, oh, I don't need to do that. I could just look at the overtone spectrum. I could look at the 0 to 2 transition of CO2, which we know is forbidden, but that doesn't mean it ever happens. It just means it's weak because the real molecule is anharmonic. And you absolutely can do that. You can probably look up what the overtone spectrum of that is. And it's going to be a little bit more complicated than just that because there's going to be a combination band as well. We can talk about that later. But nevertheless, that's just another kind of way of accessing information about higher lying excited states. You don't have to do nonlinear spectroscopy, but sometimes it's much more convenient to do that. All right, so that's an example of using a real Hamiltonian, right? No two-level system, but then discovering that when you go and write down the actual Hamiltonian in the basis, you recover the thing that you saw when you just did a simple two-level system that was with a coupling between the two states. All right? Incredible.